I couldn't focus on all the noise.
The noise I didn't even notice. I was like,
Oh my gosh.
I was.
All right. Today, reviewing for exam 2. Now, we only have 2 possible problems that you will have for the calculus question. Those 2 possible problems are either calculate the work or potential energy from a force or calculate the force from a potential energy. It's going to be one of those 2. And we talked about those last week. And so I'm just going to basically repeat the portions from last week to make sure it settles in a little before this afternoon. Good? All right. First, suppose we have a spherically symmetric potential energy function given by this function here. Question number 1, is this associated with a conservative force? I'm glad I asked. The answer is yes, because it is a potential energy. Potential energies are always associated with a conservative force. I say always. I think there are a few crazy situations, but as far as you're concerned, potential energy is always associated with a conservative force. So the fact that there is a potential energy means that there is a conservative force associated with it. And then our job is to find it. And so how do we find the potential energy or the force from the potential energy? Of course, you will have the equation sheet. I summarized the equations here. So this here is the equation to find the force from the potential energy. So here's the sad part. That is a spherical coordinate, so I have to use the spherical version of the gradient operator. So here's the gradient operator, and I'm going to use the spherical coordinate version of it right there. Okay, I said that's unfortunate, but what's fortunate? Well, here we can see everything. My potential energy is KQ1, Q2 over R. And then I have that gradient operator that's in the box. What's fortunate for this problem? What makes it so it's not going to be hard?
What constants?
Okay. All the constants. What's the only variable in our potential energy? R. So when we look at the gradient operator, we have derivatives. What kind of derivatives are those? Partial, which means?
Not related to R. Zero.
Right. So that means dd theta is going to be 0, and dd phi is going to be 0. So it's going to be easy because we only have to worry about the first one. So doing the work, there's the equation that I need to evaluate. This is the gradient operator. Notice it has direction, that's why there's a vector sign on it. And then operating on this function. So if I expand it out, There I've expanded the whole thing out. And so now we just need to do the derivatives. So what's the derivative of K, Q1, Q2 over R with respect to R?
Okay, Q1, Q2, after one.
That would be integral.
So it would be about 2, -2 over R squared plus with all the other things, right?
Okay, it's -1 because it had a power of -1. You bring down that power and then lower it by 1. And what did we say the derivative of KQ1, Q2 over R with respect to theta is? If it's a partial, 0. And what about with respect to phi? 0. Now, you haven't taken enough calculus to probably recognize that if it wasn't a partial, those wouldn't be zeros. But R could be a function of theta and phi. And so you have to do more work if it's not a partial. But if it's a partial, you're done. So there's our answer. So now, mathematically, you've learned to do derivatives. I'm pretty sure you saw partials for like the blink of an eye in your math class. And we've been talking about partials a little more in physics class, but here is, I think, our first actual application of using the partial derivatives. But as long as you remember, the partial derivative is the easy derivative, that you just treat anything that's not the thing you're taking the derivative with respect to as a constant. It should come out easy for you. So just, relax and think about what it means if that comes up. Okay, so we did the first problem. I put that first because it was shortest. Next, going the other direction. Suppose we have this function and we want to find the potential energy. If it exists, what has to be true for the potential energy to exist? That's a specific potential energy in general. It has to be conservative. So the first step you do is you check to see if it's conservative. If it's not conservative, you just say there is no potential energy. It's a short problem. If it is conservative, then it's a longer problem. So the first check is to see, is this conservative? So we check to see if it's conservative with this curl. If the curl is 0, then it's conservative. So we went over this last class period. We will do it again right here. A cross product we find by taking the determinant with our unit vectors. Now notice this is Cartesian coordinates, x, y, and z. So the first row is going to be x hat, y hat, z hat. And let me do some color coordination. The second row is going to be the first thing in the cross product, our gradient operator, which in the x direction is d dx, in the y direction is d dy, in the z direction is d dz. And the third row is our force vector. So in the x direction, it's ax squared. In the y direction, it's minus b over y. And in the z direction, it's cy. So now we have to check to see if this is 0. And this, I think to most people, was new last week. Doing this determinant, you take one row or one column, and for the case of curl, you always take the top row as your row. And you take each item in the top row and multiply it by the determinant of its co-matrix. So the co-matrix is take out the row and column of the, in this case, x hat, and I have then you subtract the second item, and otherwise it's the same. And then you add the last item. And now we have to do our math. X hat times. So when you're doing the determinant, you go like this, minus like that. So it's going to be d dy acting on cy minus d dz acting on minus b over y. So there's my first term. My second term, and my final term, no, I didn't do that right, did I? The last one should have been minus b over y here. So if each one of these is independently 0, then it's conservative. If any one of these, the x component, y component, or z component, or x direction, y direction, z direction, is not 0, then it's not conservative. So let's do the first one. What does this first one give us? That's not 0. Hence, this is not conservative. And so my answer is, it's not conservative. There is no potential energy. Notice I would have had plus 0 because the partial derivative of b over y with respect to z is 0. But the first term gave me 0, or not 0. It's not 0. If I do the second one here, partial with respect to x of y is 0. Partial, I got an extra parenthesis there. Partial with respect to z of ax squared is 0. So like Nathan said, is 0. The z direction, partial with respect to x of minus b over y is 0. Partial with respect to y of ax squared is 0. Those two are 0, but one of them wasn't 0, hence not conservative. You got a question, Michael?
So is the y hat negative because of the equation?
It's negative because of the formalism of how you find the determinant. It's positive, when you do it, it's positive the x hat minus the y hat plus the z hat.
Okay.
And Nathan was asking me yesterday, what does the determinant mean? They taught me this back in high school, and I have long forgotten what it means. I think it has something to do with like measuring the size of a matrix, but that I felt dumb. And so now I'm sharing with you how I felt dumb because Nathan asked me a question I did not know the answer to. I just know we find the determinant. We use it in lots of nifty ways. I'm sure a mathematician could nail it down. If you take linear algebra, which two of you will, You'll learn. And then you can teach me. You and Nathan. Linear algebra is in your future. I don't know what your curriculum is, if it's in your curriculum or not.
I don't even sure what's in mine anymore either.
Okay.
Oh, I wasn't. Oh, can I get
Oh, you're okay. Sorry.
just a block?
Okay, so reviewing while he's writing here, the first thing we did was we took a potential energy function and we did the gradient of the potential energy function, and that gave us, well, minus the gradient of it gave us the force. So we just had to apply the gradient function to the potential energy. Basically, you're finding derivatives. The second case, we first had to check to see if the curl was zero. We found that the curl wasn't zero, so we stopped there. You can't define a potential energy if it's not a conservative force. And the curl needs to be zero for it to be a conservative force. So now we'll go to another force and try that one. So we're going to do the same thing on this. And just like last class period, I'm going to have you guys work on it. First, determine if this is conservative. Then, after you determine if it is conservative, then find the potential energy associated with it if it exists. Yeah, I got you, Nate. Here's a piece of paper. Here's an old syllabus from last semester. I know. His stuff is actually in my office. So if you have any questions, we don't want to spend a lot of time with you thinking, I'm not sure what to do next, just raise your hand. Sure.
So, it is view this one, yeah. So, this one. Okay, I don't know if I can zero over.
Yeah. information that you're actually going to need to really should. Is this first trade?
Yeah.
So the equation is set that force not otherwise it's just multiplication. And so that can be expanded to force x to x force not force c. Okay, so this is the next one. Y component. This one has y and so there is no z cat, so it's just 0. Okay, that's fine. So then the potential energies minus the work and the potential of force not. No, yeah. So minus the below that. Sorry, it's not down. Sorry, it's dx or dl. So dl. Sorry about that. I did this. Exercise. Just arrow. You hear me make some beats that I have no idea what it is. It's not my electronics, it's something else. Okay, so DO is, adjusting the distance, and it's x half to x plus y half to y.
This is the middle for that. This is the middle for
So, you have we have 2x cubed x hat plus 4y hat dot. Right, we don't need because it's going to be 0, right? And so that simplifies to integral of the x hat and x hat, y hat and y hat. And then, plus integral of 0. And so it does come out to this, but I want to make sure you have the way it gets there. And then remember, potential energy is minus this integral. It's actually changing potential energy as well. So potential energy minus. No, it's just x hat dx. So cross out this here. No. This one. Cross that. And then it's x hat dx. That's why I have to go. This is right. If you did never.
I'm doing that for different sheets.
That's going to happen. It's fine. That's good.
And so I did the practice exam, and I was doing solutions on that. And for some reason it was like generalizing, which I didn't really understand.
Okay, so all that's doing the same. This was changing potential energy.
Yes.
So that means this is potential energy final times potential energy initial. So the two finals are potential energy final, which is initial, potential energy initial. And so then this is final divided by final next one, which is say, well, at any point, instead of final, which is say, at any point.
So I can just, okay.
But you did.
Okay.
You did early.
That's interesting. Generalize it. Okay.
So since you're doing PHYS, you have at least part of acceleration because it's acceleration. So you have integral of 2x cubed dx, and then of y corresponds with y, so you so what is this? This cancels. Minus this. This is a partial perspective. That's a line. So
It isn't.
so it's that's 2x. So they're all zero, so it's conservative. And then you go on to the last part, which is finding potential energy. So, potential energy. Two of the four of you, are you done, John? Or- Okay, so all but one is done. So let me go over this with everyone now, since all but one are done. That way it's teaching one person confirming for the others. So the first thing we did was checking del cross F. I'm going to show you now a shortcut. If each function, or if each item in the lowest row here is only a function of its variable, that is in the x column, if it's only a function of x, the y column, it's only a function of y, z column, it's only a function of z, it's going to be conservative. It's going to be conservative because you're going to have partial derivative with respect to something else of something with x, and so on. So if you have this and this together and none of the other variables, it's always going to be conservative. So that's a quick shortcut. If it's not that way, it doesn't have to be non-conservative. You can't say, oh, there's a y in my x hat direction, it's not conservative. Because if you have an x in the y hat direction, you could have the two work out to still be conservative. So it was a conservative force because when you did this, dy or ddy of 0, ddz of 4y cubed, those were 0. ddx of 0, ddz of 2x cubed, 0, and ddx of 4y cubed and ddy of 2x cubed, 0. So then we have to do finding the potential energy. Definition of change in potential energy is minus work, and work is integral of force dot dl. Now I put the limits here because this is exactly correct. If I want to find the potential energy in general, I can save myself a little bit of hassle by dropping the limits and just saying potential energy is equal to minus the integral of force dot dl without limits. Then I'll just get my potential energy function. So when we do this, that's going to be integral of, and I have to write down my force equation, 2x cubed x hat plus 4y cubed dotted with, y hat, forgot the y hat, dotted with x hat dx plus y hat dy plus z hat dz. Dot product means you're multiplying the parallel parts. So x hat is parallel to x hat, y hat is parallel to y hat, z hat is parallel to z hat. Question, Caitlin?
Where did the negative go?
It was a mistake on my part. Thank you. I could point it out in others, and I make the mistake myself because, hey, we're all human. So since the x hat is only parallel to x hat, this becomes the integral of 2x cubed dx, put the minus sign out there, put a parenthesis, plus 4y cubed dy. And I'm not going to put plus 0 dz. It doesn't make sense to put plus 0 dz. Now, I saw some signs that were different. You see that I forgot a minus sign, so I understand that can happen. On the test, if you have something like this, you probably won't have to worry about the sign being dropped here or there because the question, I'll probably have the signs consistent. So we just do these integrals.
So you broke them up into two parts.
Yeah, because of the dot product. Yeah. And so there should have been my correct potential energy function. I'm going to check this. Why? Because I'm that kind of person. How am I going to check it? Minus del of the potential energy, or minus the gradient of the potential energy, should be my force. So I'm going to do this calculation. Now notice I have minus signs everywhere. Multiply those through and they become plus signs everywhere. So I'm going to have derivative with respect to x, partial derivative with respect to x is going to be, well, let me be really stupid. Why did I call that really stupid? Yeah, because derivative of y to the fourth with respect to x is 0. That's because it's a partial derivative. So I didn't really need to put that in there because I could in my brain instantly say, well, that one's 0. And so that's going to be derivative of x to the fourth is 4x to the cubed. And then I'm going to have plus y, let's change colors, plus y hat d dy of and now partial with respect to y of x to the fourth over 2 is 0. Why do I have a 3 on bottom instead of a 2? It's a very good question, huh? So that's equal to 2x cubed in the x direction plus 4y cubed in the y direction. And so we worked our way back, hopefully, to the same force we started with. Yes. Any questions about the processes we went through today? Either the taking the gradient of the potential energy to get the force, like I did starting and ending, or finding the curl to see if it's conservative, or doing the integral for work to find the potential energy. Any questions about those items?
So for the work for potential, the one that you just did,
Yeah.
you'll follow that similar formula with what is it, potential change in potential energy is equal to negative W equals the integral of force times d.
Force dot.
Force dot d.
Right, it's dot product. It's really important that it's a dot product.
Okay.
If you just do times, you're going to get a different answer.
Okay. So dot product would be
Parallel post.
And what?
Parallel post.
parallel.
Yeah,
and
parallel
then
parts.
Cross would be perpendicular.
Perpendicular parts, right.
Okay.
And the cross product, as you saw, you use that determinant to do the cross product.
Okay.
So you know how when we did the table layout, you said if like in the x hat category there's only x, they'll all equal 0, so it will be a thing.
Yeah, if the x column has only x in the force function, the y column has only y in force column. The Z column is on Z and force.
So if it does, so if we just see that, we're like, okay, good, move on to the next
Yeah,
approach.
make sure you write down for explanation, because if you're going to have it graded on your work, you want to write down, this is 0 because, and not just, magic happened.
Okay, thanks.
So,
In the cross, or you still?
Yeah, but if it has like a Y in the X, it doesn't necessarily mean it won't equal 0.
right. If it has the Y and the X and the Y, it's possible that it could still be 0.
But would it have to have the opposites in each one?
It would have to have, yeah.
But if it was a D.
So if it was just 1, then it's,
Okay, yeah.
So if it was a cross product, how would it differ in the table than a matrix table? Like if it asks for a cross product equation or a situation, how would the tables differ? If you know what I mean, like.
the cross product, the standard way, now we have other ways, two-dimensional instead of three-dimensional cross product, it's done more simply. But if you have a three-dimensional or higher dimensionality cross product, that is the way you do it, always with the matrix.
Okay.
Like I said, two-dimensional, which is almost everything we do in physics class, we can do it simpler. If you don't have any more questions on this, any questions about the test in general, because we don't have to talk only about calculus here.
That's what. So how is the grading for this test going?
So I will grade it just like I did the last one. I show you what the scan is when you walk out the door. Remember, the scan only tells you how many right or wrong you got. It doesn't tell you your score because they have different weights for different problems. If on the last 3, if you don't get them all correct, you can ask me to grade the last 3 based on partial credit. It's either all 3 or none of them. And I'm not going to say, oh, he asked me and he got lower, so he gets a lower grade. I'm not going to do that. There's no jeopardy in asking. But if it's graded on partial credit, then I will give you 2 points if you have an appropriate figure to help you solve the problem. Right? A figure that doesn't help you solve the problem isn't going to get you those points. And then 3 points for explanation of the process. So for instance, for the problem we just did, say, I'll calculate the curl to see if it's conservative. If the curl is 0, then I will integrate the work equation, work is F dot dl, and set the change of potential energy is equal to the work. You would have to have that explained there. Right? You don't need any more words than what I just said. But you do have to have, this is the way I'm going to do it. And that's 3 points. Then you need to have your equation, so you would have del cross F equals curl. Del is equal to this, You don't need to write down force because that would, of course, be given to you in the beginning. And work is equal to force dot dl. dl is equal to this. All of that stuff is in the equation sheet. Just identify which equations they are. And so that's 2 points for writing that. And then the last 3 points, 2 points for doing the work correctly, and 1 point for getting the right answer.
Do you just want the equations part, the equation written down, or do you want the variables defined?
No, don't use define, just the equation written down.
Okay.
That
might take a while.
If you don't know what the variables are, you're not going to do it right for the work part anyway, right? And there are people who do that. They'll pick an inappropriate equation because they don't know what the variables are. And it said R, and so they just chose the equation. It happens. Other questions?
It is 2 hours long.
Yes. All right. Well, we'll leave 5 minutes early. Makes up for last week because didn't we leave like 5 minutes late last week? I think we did. So.